In the previous lecture, we started with Frobenius' formula for the determination of simple characters corresponding to some irreducible representation of Sn and converted that into a graphical method. Let me quickly recapitulate what this graphical approach for the determination of characters for an irrep of Sn happens to be. For this, you have to start with a Young diagram, which is basically a set of boxes stacked in rows. And this is the Young diagram corresponding to the partition which labels the particular irrep you are interested in. For example, the diagram that you can see on your screen right now corresponds to the partition which has 6 and 6 and 5 and 4 and 3 and 3 and 2 and 2. And all of these add up to produce the number 31. That is, this Young diagram will be useful in determining the character for this particular irreducible representation, an irrep labeled by the partition 6 plus 6 plus 5 plus 4 plus 3 plus 3 plus 2 plus 2 of S31. Now, to determine the value of the character corresponding to a class labeled by the cycle structure 1 to the alpha, 2 to the beta, 3 to the gamma, etc., what we have to do is carry out regular applications of alpha 1 dots, beta 2 dots, gamma 3 dots, or triplets of dots in succession. Now, this application can be done in any order that you want, but in the end, you will have to apply all the dots and find out all possible ways in which this particular Young diagram can be filled, staying within the rules for this so-called regular application. And the rules for this is what I am going to outline now. At any given stage, what we need to do is add a number, say R, of dots to the existing tableau. So this corresponds to a multiplication in particular by SR. Now, the rule for this would be you have to begin at some row. Let us just say, for the sake of argument, that we need to begin perhaps at this particular row. And what I am going to do is add enough dots to this row so that I have one more dot at the end than in the row immediately above it. In this case, since the row immediately above this one has a single dot, I can only add enough dots to this particular row to make the total number of dots on this row equal to 2, which means I can add at most one more dot to this. Then I am supposed to move on to the upper row and continue. When I say continue, I mean I keep on adding dots to this upper row until I exceed the number in the row above that by 1. In this case, I can add 2 more here. Then I move on to this row, I can only add 1 more dot here. When I move on to this row, I can add 2 dots here. And then I have to add, say, 1 more dot here, then add enough dots until I run out of the number of dots I needed to add. So in this case, for example, suppose I had to add 8 dots. That is, I was considering a multiplication by S8. This is exactly how I would go about doing it. Now, the important point is you have to stay within the bounds of this diagram. So, suppose I had 10 dots to add, then I would have to actually go beyond this. So, this particular regular application would not really be a valid one. Now, another very important rule is the final diagram you get after all the R dots have been added must be a valid Young tableau. What that means is that the number of filled boxes at any given row must not exceed the number of filled boxes in a higher row. So just to sort of illustrate why this is important, suppose I had only 5 dots to add. Maybe I was multiplying by S5. which means my procedure would have ended here after adding 5 dots. But now I end up with a tableau in which this particular row has 4 filled boxes, which is more than the number of filled boxes in the row above it, which is clearly 3. So if you stop at a stage like this, then your particular application is not a regular application and it's not a valid thing to do. In other words, you will not be able to start in this row and add 5 dots in this particular case. So what you have to do is keep on adding dots in this way until all the regular applications have been done. Figure out all possible ways in which you can fill up the Young diagram while adhering to these rules. Staying within the boundary of this diagram, as well as having a valid Young tableau at the end of each stage of this process. Then the only additional rule you must remember is that this regular application, okay, by the way, this one is not, so let's go back to a situation where you do have a regular application. Suppose I went back to this original case with 8 dots. Now, if this regular application involves an even number of rows in your Young tableau, then you get an additional factor of -1. In this particular case, the number of rows that have been affected is 1, 2, 3, 4, 5 and 6. Since 6 rows have been affected, you have actually affected an even number of rows. This is called, somewhat confusingly, an odd application. The odd here really comes from the fact that if you went back to your original picture of multiplication by SR, this particular application would involve a permutation of an odd number of elements. Anyway, what you have to remember is that in case your application affects an even number of rows and hence is an odd application, you incur an extra minus sign for that. So you have to take care of all the minus signs you accrue until the entire Young diagram is filled. And if you have an even number of minus signs at the end of the day, of course that gives you a +1. If the number of minus signs you acquire this way at the end is odd, then you get a -1 for that particular filling. So take all possible ways of filling up the Young diagram while adhering to these rules and count the numbers that you have, remembering to put a factor of -1 for these kind of fillings where you have an odd number of even rows being affected, and finally add them all together and you have got your final character corresponding to this particular class, which involves this 1 to the alpha, 2 to the beta, 3 to the gamma cycle structure for this irrep. Let me now illustrate this with a specific example. So what we are going to do is we are looking at the irrep 5,2,1 of S8. This of course means the irrep which corresponds to the partition 5 plus 2 plus 1 equals 8. And of course this has the Young diagram given by 5 boxes in the top row, 2 in the second and 1 in the third. And then we are going to look at the value for the character corresponding to this particular class. 3, 2, 1, Q. 3 1 cycles, 1 2 cycle, 1 3 cycle. Now, if you apply S3 first, then there are various ways of doing this, sticking within our rules. You can of course apply all 3 dots to the first row. Then you could start at the second row, put in 1 dot and 1 dot only. Remember, at this stage we have not put in any dots, so let's start with a blank thing and show you how this goes. You put 1 dot here, which is already 1 more than in the previous row. So you stop adding dots here. Then you put the rest of the dots in the top row. By the same token, in this case, we will start from the third row. That's already 1 more than the second row. 1 more here. 1 more here. Now in this case, you can get a minus sign and this one will give you a plus sign. 2 rows affected, 3 rows affected. Our rule that we stated a while ago. But for the time being, I will not bother about the signs. I will just put in the signs at the end. So, next we are going to put in S2. Now, I have written these as 1, 2 and 3. And the labels here are just to show descendants. 1, 1 is the first descendant starting from this 1. 1, 2 is the second choice, which you start from 1, and what else can you do? And so on. Now, S2 means you have to add 2 dots. Now, if you are starting from 1, 3 red dots. I've changed the color here, but let's assume that you have red dots only in the whole picture. Now, I can add 2 green dots now. Where can I add the 2 green dots? I can, of course, add them at the top. That's an allowed thing. Can I add them here? Of course, I can add them, and I will keep on adding them until either I run out of dots or run out of the boundary of the thing, or I exceed the number of dots in the previous row by 1. Now, of course, the number of dots in the previous row is 3, so I can't exceed that. But I can definitely fill up the 2 boxes here by 2 dots. Nothing wrong there. Now, finally, there's one more possibility. Starting from 1, I can also do one more thing. I can start in the third row, put 1 dot. Remember, there was no dots, that is no green dots for the second, green for the second application of dots. There were no dots in the second row, so now I can put a green dot here, and I can add 1 more green dot here. Now I'm out of dots, and this is done. What about this? This has 3 red dots like this. I can, of course, put the 2 green dots here. But that's all. I can't do anything more. Can I start here? The answer is no, I can't, because I have to put at least 1 more dot than I had in the previous row, but I can't do that because the bounds of my Young diagram does not allow me to put 2 dots here. The same goes for adding dots here. I would have to put at least 1 more than in the previous row. That is, I have to end up with at least 1 more than in the previous row. I already had 2, so I would have to end up with 3 if I wanted to start here, but I can't, because the Young diagram will not allow me to put in 3 dots on this row. So there's only one descendant of 2, which we are calling 2, 1. For 3 dots down this column, I have this possibility, of course. I also have this possibility. I can put a green dot here. Remember, that has exceeded the number of dots in the previous row before, of course, application of this particular green dot by 1. And then we can finish off by putting in 1 more green dot here. So that's 3, 2. Now I have finished S3, S2. I need to put in the 3 S1s. So let's look at S2. This had 6 possibilities. The 1, 1, for that, I can only put in the next dot, the purple dot, in one location and one location only. I can put it just here. That is, I can lead to this. There is no other possibility. I cannot put the purple dot here because that will not give you a legitimate Young diagram. You will have more dots in the third row than you have in the second. So 1, 1 only gives you 1 more. That's 1, 1, 1. 1, 2, on the other hand, has multiple possibilities. You can put a purple dot here, which is a perfectly legitimate thing to do. You can also put a purple dot here. So you have 1, 2, 1 and 1, 2, 2. 1, 3, 1, that is the first descendant of 1, 3 would mean that you put a dot here, which is legitimate. But you also have 1, 3, 2, you can put a dot here. Then we come to the descendants of 2, 1. Can now have 3 possibilities for putting the dot. You can put a dot here, not violate any rules. Put a dot here, you can put a dot here. So you have 3 possible descendants. 3, 1 has 2 descendants. You can put a dot here, you can put a dot here. And finally 3, 2. There's only one place where the dot can go, which is here. 3, 2, 1. Done. So now we see we have already got quite a lot of possibilities. At this stage I have exactly 11 standard young tableaus, but we are still not done. The next application of S1, well, with 1, 1, 1, you have two more places. The orange dot, which signifies this next application, can go either here or here. So 1, 1, 1, 1 and 1, 1, 1, 2. From 1 to 1, you again have two possibilities here and here. 1, 2, 1, 1 and 1, 2, 1, 2. For 1 to 2, you have only one possibility. That's just 1 to 2, 1. 1, 3, 1. Two possibilities again here and here. 1, 3, 1, 1 and 1, 3, 1, 2. Now 1, 3, 2, of course, has only one place for the orange dot, that's here. That's 1, 3, 2, 1. The only descendant you have of 1, 3, 2. 2, 1, 1, two descendants, one here, this and this. 2, 1, 2, two descendants, one here. 2, 1, 2, 1 and 2, 1, 2, 2 in your diagram. 2, 1, 3. Again, two possibilities. Here or here, and 3, 1, 1, two possibilities again, here or here. Here gives the, adding an orange dot here gives you this, adding an orange dot here gives you this. 3, 1, 2, only one possibility, 3, 1, 2, 1. And 3, 2, 1, again only one possibility, you can only put the dot here. Now finally you have to finish with the final dot. Now I'm not going to bother doing that because there's only one square left and one dot to go, so there's only one way to do all of that. So you can imagine that each of the empty squares here have been filled up by a dot. So these are all the terms that actually contribute. There are precisely 15 of them in this way of doing the calculation. That's quite a lot, but you have to also remember that there's an issue of signs. Now, the signs involve the idea of even or odd application. At any given step of the process, have we applied the dots to even number of lines leading to a minus sign or odd number of lines leading to a plus sign? Here, of course, we are only to worry about the red dots and the green dots. The purple and the orange dots have been applied only at one square at a time because they were S1 applications. Now this one, of course, has a plus sign because the three red dots have gone to an odd number of lines, namely 1. Both green dots have also gone in one line. Same here. Same here. 3 red dots on one line, 2 green dots on one line. Same here. Same here. But now 3 red dots on one line, 2 green dots on 2 lines. So overall a minus sign. Minus sign again for the same reason, minus sign for the same reason. Here you get a minus sign from the red dot applications, a plus sign from the green dot applications. So you get a minus sign again, again, again. Now we have 3 red dots in 3 lines, that's an even application, odd number of lines, and 2 green dots in 1 line, again an even application, so plus, and here you have a minus. The 3 red dots give you a plus 1 because they are on 3 lines, but the 2 green dots being on 2 lines give you a minus 1. So out of the 18 young diagrams that you have, 8 come with a plus sign and 10 with a minus sign. And therefore, when you add them all together, you get the corresponding character of plus 8 minus 10, that's minus 2. So this is the character for this particular class corresponding to this particular array. Now remember, in order to calculate this, we have to start with D and then multiply by SL, where SL is S3, S2, S1 cubed. But I could have done these multiplications in a different order as well. Would that have changed the result? Of course not. But, as we will soon see, doing the calculation in a different order might substantially increase or decrease, as the case may be, the efficiency of the process. So a judicious choice of order actually helps us cut down on the effort a lot. In this particular example, what we did was multiply by S3 first, then by S2, then by S1 thrice. We could have started by multiplying by S1 thrice to begin with, that is multiplication by S1 cubed, one after the other. In fact, the three dots that we have here are black, green and blue. Black for the very first S1, green for the second one, blue for the third one. It's pretty easy to see that after you multiply by S1 cube, you have ended up with only 4 possibilities. Black, green, blue all in the first row. Then you could have black and green, blue here. Or you could have black and green like this, and then you have 2 possibilities for the blue, one here, one down here. Now let's come to application of S3. Now, for this particular diagram, that is when you have already reached this stage, I cannot put 3 red dots here for the S3, simply because I will be going out of the bounds of my partition or out of bounds of the Young diagram. What we can do is start here, add a single dot, that is one more than what we have. Then the other 2 dots for the S3 will go here, and that leads to a legitimate diagram. We have run out of dots to put in, but what we end up with is a legitimate standard tableau. Could we have done this by starting from the second row? Well, not really, because I would end up adding as many dots as I have to in order to exceed this, or until I run out of dots. But in both the cases, I cannot of course add as many dots as I need to go one up over this one, because I don't have 4 dots to play with. But more importantly, even with 3 dots in this row, I would have gone beyond the boundary of this particular partition. So, only one possibility comes from here. What about this? Here I can only put in 3 red dots here, but that's the only possibility. Note that I cannot start here, because if I started here, I will not be able to go one up on this row. Same here, if I started here, I cannot go one up on this previous row, simply because I'm going outside the Young diagram this way. So I have only one thing that comes from here. Well, what about this one? Again, only one possibility. 3 red dots on the top row. Now this one gives you 2 choices. 3 red dots all on the top row. Or you could start from the second row. If you put 1 here, that means you've got 1 more than in the previous row. And then I have to go on to the previous row and keep on adding dots. And here I put in 2 dots. So that's a legitimate thing to do. Now finally I need to add S2, 2 more purple dots in this case. So 2 purple dots here is fine. I cannot add the 2 purple dots to these 2 boxes. Remember, the rule is, if I start here, I have to add at least 1 more than in the previous row, which I can't. I can't have 2 dots here. By the same token, I cannot add 2 dots here. You have only space for 1. So this one actually has no descendants. Neither does this. The only other possibility is these 2. So you have only 2 diagrams left after the whole process. Contrast this with 18 in the previous example. And now for the signs. This one has red dots spread out over 2 rows. The purple ones are in 1 row. But you have 1 minus 1 from here. Here, again, red dots are spread over 2 rows. Purple dots are in the same row, so another minus 1. So both of these diagrams come with a minus sign, so our character is minus 2. Notice how much simpler this calculation was compared to the previous one, simply because we applied the dots in a different order. But the result, of course, was one and the same. After this demonstration of how to apply the graphical method to determine a specific character, let us see whether we can draw some more general conclusions using the graphical approach once again. We will begin with a very special and simple example. There are 2 particular partitions of n for which the corresponding irreps turn out to be very simple. In fact, these are the 2 one-dimensional irreps which every Sn has, and they correspond to the two partitions, one in which the number n is written as just equal to n, and the other in which the number n is partitioned into n ones. So the corresponding Young diagrams for these two partitions are shown on your screen right now. N corresponds to n boxes in one single row, and 1 to the n corresponds to n boxes, but this time 1 in each row, so you have n rows. Now, it is very easy to determine the character corresponding to every class for these two particular partitions, or rather for their corresponding irreducible representations. First, let us take a look at this. Now, no matter which class you are talking about, say if the class is 1 to the alpha, 2 to the beta, and so on, here there is obviously only one way to fill this diagram up. You will have to put all of the dots, the alpha single dots corresponding to S1 to the alpha, then the double dots, beta of them corresponding to S2 to the power beta, and so on. They have to all go exactly in this one row, and so for each and every class there is only one corresponding diagram, and that diagram must come with a plus sign for the simple reason that in each case exactly one row is being straddled, no matter which one you are talking about. If you are talking of the beta 2 cycles, so corresponding to beta pairs of dots, each of these pairs have to go to that one row, and therefore it's an even application, an application which straddles an odd number of lines. So for this, no matter which class we are talking about, the corresponding character will simply be +1. That's sort of obvious. This is the identity representation for Sn after all, and for this representation, every class or every element is represented just by the simple number 1. Now, what is the case with the other one-dimensional representation? The one corresponding to 1 to the n as a partition. In other words, the one for which the Young diagram is n boxes in one column. Here again, it's easy to see that there is only one way to fill up the boxes. You have to put them in one vertical line, one after the other. There is no other choice. So basically, you are going to get only one Young diagram. The question now is, what is the sign corresponding to this particular thing? Here, you have to realize that, say, if you are looking at a 2 cycle, a given 2 cycle will straddle 2 rows. Another 2 cycle will also straddle 2 rows. So, every 2 cycle will give you a minus sign. Minus sign because it's an odd application, one which straddles an even number of rows. On the other hand, every 3 cycle will straddle 3 rows, giving you a plus sign. Every 4 cycle, if present, will straddle 4 rows and therefore will give you a minus sign, and so on. So in the end, will you end up with an overall plus or a minus sign? That depends exactly on the number of even cycles which this particular permutation, or which every permutation corresponding to this particular class has. So if the number of even cycles happens to be odd, then you will end up with odd number of minus ones, and therefore you will get a minus 1. Otherwise, you will get a plus 1. This, of course, should be very familiar, as this is exactly how the alternating representation of Sn works, but it is gratifying that our rules for the graphical determination of characters bears out this rather well-known thing. Let us now move on to some slightly more complicated partitions than this. The first of these irreps that I am going to consider corresponds to the partition n-1 plus 1 equals n. So, the corresponding Young diagram will have n-1 blocks in the first row and 1 block in the second row. The question is, if you consider a class corresponding to cycle structure 1 to the alpha, 2 to the beta, 3 to the gamma, and so on, can we figure out the character corresponding to that class for this irrep using the graphical method? It turns out to be rather easy to do this. Remember, all we have to do is apply single dots alpha times, double dots beta times, triple dots gamma times, etc. so that we can fill up the entire Young diagram, adhering to the rules that we had laid down before, and then simply count the number of such possible filling ups or possible tableaux, taking into account, if necessary, the plus or minus sign which comes in. So now let us check how many ways can we fill up this particular Young diagram using alpha 1 dots, beta 2 dots, and so on. Now, notice that putting all alpha 1 dots in the first row is not possible, because once you put all alpha 1 dots in the first row, then you have only a single box left in the second row. But remember, if you are going to start at the second row and you have either the beta 2 dots or gamma 3 dots, etc. to fill up here, you simply cannot put enough dots so that you can go beyond the number of dots in the upper row. But that is a very important thing that you need to do. Remember, this has only one box, so you cannot put in 2 dots or 3 dots here, because you're going to then go outside the boundary of the Young diagram. So the conclusion is that the only way in which you can have a proper filling up of this Young diagram so that you get a valid Young tableau at the end is that you will have to put one of the dots, of course, the very first one of the alpha dots has to go in here, but in the end there will have to be one dot among the singlets in this lower row and alpha minus one of them in the upper row. Now, exactly how many ways is it that you can do this? That depends on which one of the alpha dots go here. Remember, the very first dot that you put in, the first of this alpha dots that you're putting in, alpha 1 dots, that has to go into this corner. So there is no choice for that. Any one of the subsequent dots can go here and the rest would go here. So you could have the first dot going here, then the second dot, then the third dot, but the fourth dot going here. Or you could have first dot here, second dot here, third dot here, fourth dot here, and so on. So this particular dot could be any one of the alpha minus 1 dots. Alpha minus 1 because the very first one has to go in the top corner. So basically there will be exactly alpha minus 1 possible diagrams, and in all such diagrams the sign will be plus 1 simply because any one of these multiple dots that are being applied at any given stage, that could be happen only because of these 2 to the beta or 3 to the gamma terms, they would all have to go in the top row, so they would all have to straddle exactly one row. Odd number of rows, hence plus sign. So alpha minus 1 possible fillings, each one of them gives you a plus sign. The corresponding character here has to be alpha minus 1. So this gives us a general formula for each and every class. If you are looking at this particular irreducible representation, the one corresponding to n minus 1 plus 1, the character is always alpha minus 1, 1 less than the number of 1 cycles. There are 2 points about this calculation that I should stress at this stage. The first is that this whole calculation, of course, starts with taking D the determinant form and then multiplying it by S of L. And there, what we have chosen to do here is multiply by the alpha S1s first, then multiply by the beta S2s and so on. As I have stressed before, the order in which we do these multiplications does not really affect your final answer. However, the ease with which you get to the result may very well depend on the order which you are using. In this and the next two examples where we will calculate characters for all classes for specific irreps, we will follow this particular order. All the S1s multiplied first, then all the S2s, then all the S3s and so on, which essentially means that we are going to put in alpha 1 dots to begin with, then beta 2 dots, then gamma 3 dots and so on. The other point is slightly more subtle, but those of you who have been paying attention may have already caught on to that. This argument that I have given right now works fine for all values of alpha except 1. If there are no 1 cycles in your class, that is, if alpha is 0, then this argument that you have to fill up the first column with 1 dots and then put the rest of the 1 dots in the first row, leading to this number alpha minus 1, that really does not work because there are no 1 dots to put in here. However, in such a case, if there are no 1 dots, you are going to start with either the 2 dots if there are any, or the 3 dots if there are any. In general, you have to start with some cycle which is larger than a 1 cycle. And in such a case, the filling will have to be in the following manner. You will have to start here and then put the rest of the dots belonging to that particular cycle, maybe a 4 cycle, as the case may be, in the top row. Then go on to fill the rest. Remember, the very first thing that you fill cannot all go into the top row, because if that happens, you are actually leaving no space to put in the next dot. Now, of course, if you do this, then all the subsequent applications will involve 1 row and 1 row only and will give you a plus sign. But this very first application of 2 or more dots will involve 2 rows and will give you a minus sign. So there will only be one possible diagram and that will come with a minus sign. Hence, our character in such a case would be just minus 1, which is consistent with this formula alpha minus 1 given that alpha is 0. Such special cases will also arise in the arguments that we are going to present for the next 2 examples. I am not going to state them explicitly, but you should be able to figure out which are the special cases for which the arguments we are presenting do not really work as they stand. But you will also see, if you work it out carefully, that in all such cases the general formula that we derive will keep on working despite the fact that you have to argue differently to get at the result. Let us now move on to a slightly trickier example of this kind. We are going to look at a partition n minus 2 plus 1 plus 1 for n. In this case, the Young diagram has n minus 2 boxes in the first row and then 1 box each in the second and the third row. Compared to the previous one, there are more ways of filling up the dots for this particular diagram. For example, it's easy to see that one possible situation here is that all the alpha single dots can go into the top row. This was not a possibility for the previous case. But if that happens, then what you can have is that 2 dots corresponding to a 2 cycle can go in the second and the third row. it's easy to see that you cannot start at a second row because it will not be possible for you to put in one more dot than in the previous row. Remember, even if you had only one cycle, this corner is definitely already filled by that. So, the 2 cycles that you are talking about, the 2 dots for that can not start here, because if you started here, you would need to have at least one more than in the previous row, which is impossible. But you can start here, one more than the previous empty row, and now put in one more here. So this is a perfectly valid, legitimate application. However, you have to realize that if you had beta 2 cycles, any one of the beta pair of dots could have gone here. So there will be exactly beta distinct terms of this kind. Now each of these will come with a minus sign because the doublet here is straddling 2 different rows, and so this will contribute minus beta to the overall character. However, that's not the complete answer because there will be other ways of filling up the diagram. Now, what is very easy to understand is that if you do not put all the alpha single dots on the top row, then you have to actually fill up the second and the third row as well with single dots, because if you just filled up one of them, it would be impossible to then fill up 2 dots or 3 dots, maintaining our rules. So this is a possibility. All of these 3 boxes in the first column are filled with the singlets. Of course, the rest of the single dots will have to go in the top row, and then you have no further choices. Then all these beta pairs, gamma triplets, all of them have to go on the top row. Each of these diagrams obviously will contribute +1 because all these multiple fillings, the ones which could possibly have straddled multiple rows, all of them are obviously going into the top row, each in one row. So the sign is obviously +1. The question is, how many such terms can you have? The answer to that is rather simple. Of the alpha single dots that we can put in, one of them has to gain the top corner. So that means out of the rest, there are alpha -1 choices for what this one will be. However, it's slightly more complicated than that, because if the second dot goes here, then you have alpha -2 choices for the third dot. If the third dot goes here, then only subsequent dots can come in the lowest position. So for that, the number of choices is alpha -3, and so on. If the alpha -1 dot goes here, then there's only one choice left. The alpha dot has to go below. So the total number of possible choices is alpha -2 plus alpha -3 all the way up to 1, or alpha -1 into alpha -2 by 2. There is another way of looking at it, which is perhaps simpler. After the top corner was filled, you had alpha -1 single dots to put in, and you can choose any 2 of them, and once you have chosen 2 of them, any such choice will correspond to only one possible diagram, because whichever one of them came first has to go in the second row, whichever one of them is later goes into the third row. So basically, the question is, in how many ways can I choose a pair of dots out of alpha -1 choices? Alpha -1 because 1 has already gone into the top corner. So the number, of course, is alpha -1 C2, which is just another way of seeing this answer. So the character corresponding to this particular irrep, n-2 plus 1 plus 1 being the corresponding partition, for any class is simply dependent on the values of alpha and beta, the number of 1 cycles and 2 cycles. You should realize that for such a partition, it's impossible for the character to depend on the number of 3 or higher order cycles, because for them there's only one choice. They all have to go into the top row. There is no other possibility. Our next example involves the partition n-2 plus 2 of n. Corresponding Young diagram obviously has n-2 boxes in the top row and 2 boxes in the second row. And once again, the question is exactly how many ways can we fill up this Young diagram with the alpha singlets, beta doublets, gamma triplets and so on, adhering to our rules and counting the number with possible plus or minus signs to get the character. Now, as in the previous example, here too it's possible to put all the alpha single dots on the top row, but then it's obvious that the only possibility left is that you will put the one doublet down here, one of the beta doublets. Now in this case, both of these pairs go into one row, so this is an even application, one involving an odd number of rows, and therefore it's going to contribute plus 1. How many such diagrams can you get? You will get one for any one of the beta choices that you have here. Out of the beta doublets, any one of them could be sitting in the second row. So there are exactly beta such diagrams. So that's going to contribute plus beta. Now, if all of the alpha singletons were not sitting in the top row, what are the possibilities? Of course, then you must fill this up, but it's easy to see that once you have done that, you must actually fill all of these up. The question now is, out of my alpha minus 1 singlets left after you fill up the corner, in how many ways can I fill up this thing in this particular pattern with 2 of the lower boxes filled? And here the question is simple. Which one of the dots actually go into the lower row? And the answer is simple. You can do it in exactly alpha minus 1 into alpha minus 2 by 2 ways. Just the same argument as the one we gave before. But there is one catch. Out of all the possible pairs that you can have after you take the first one out to go and sit in this corner, there is one which cannot really be put in according to our rules. Because your second dot can very well sit here, but if your second dot sits here, the third one cannot be here, because at that stage you will get a non-valid Young tableau. Of course, if instead of the third one sitting here, third one went here, but the fourth, fifth, sixth, any one of the later ones went here, there would be no problem. So out of this possible pairs, the only pair which is not allowed is 2, 3 going in the lower row, which is why you have to subtract 1 for that particular choice, which is not a valid diagram. So number of valid diagrams you have in which all of these are filled up is given by alpha minus 1 into alpha minus 2 by 2 minus 1. Of course, each one of them come with a plus sign simply because the doublets, triplets, etc. all have to sit in the top row now. So far, we have been looking at specific partitions and hence specific irreps of Sn and trying to answer what are the characters for each and every class. Let us look at a slightly different question now. We are going to look at a specific class, the class corresponding to a single n cycle of Sn, and ask, can we figure out the characters for each and every irrep corresponding to this particular class. So if you think in terms of the character table, so far what we have been doing is looking at specific rows of the character table, and the formula that we had figured out here would have filled up the entire row. Now we are asking about one specific column, the column corresponding to a single n cycle, and we are asking, can we figure out the entire column? The answer turns out to be yes, and it's really rather simple to figure out. Notice that because your class has a single n cycle, you have only one regular application to do, that of n dots, which will fill up all of these n squares. Now, there are two distinct situations here. One in which you have p such boxes in the first row, and the rest of the boxes, the n minus p boxes, are all in subsequent rows. So, basically, what you have is a L-shaped Young diagram. Now, this entire thing has to be filled up by dots, and it's easy to see that the only way you can do that is start from the very bottom and keep on filling up one box at a time. Remember, prior to this filling up, the previous row was empty, so you can of course legitimately put in one dot there, and now once you reach the top row, you can put in all of the rest and complete the diagram. So basically there is only one diagram that you are going to get. The question of course is, do you get a plus sign or a minus sign? And the answer to that is exactly how many rows are straddled. Notice that the number of rows straddled is simply the number of elements in this column. And that of course is n minus p for the lower boxes plus 1 for the top one. So the sign will be minus 1 if n minus p plus 1 is even, or n minus p is odd, and plus 1 if n minus p plus 1 happens to be odd. So the character here is simply minus 1 to the power n minus p. So for all such irreps, the irreps corresponding to partitions like this, namely 2, 1 to the n minus 2, 3, 1 to the n minus 3, in fact even 1 to the n, for all of them, this formula is going to work. Now what about any other irrep? Any irrep which has a different shape. That is, any irrep for which there is at least one row below the top row which has more than one box. Now once again, let us ask, in how many ways can we fill this particular Young diagram up, adhering to our rules? Of course, you have to start at the very bottom because every box has to be filled. And as you go up to now you are adhering to the rules. Now you have to put in as many dots here, which is one more than the upper row. That means here, since the upper row was empty, you can put in only one dot. But if you do that, if you don't fill up this other dot, it's impossible for you to put n dots in the n boxes. In other words, there will be no valid diagram corresponding to these partitions at all. And so, the character corresponding to these other partitions will all be 0. So, for this particular class, which typically is written down in the last column of your character table, the characters are just plus 1 or minus 1 for some of these partitions which correspond to p elements in the first row and one element each in the rest of the rows for the Young diagram. You will get minus 1 to the n minus p. For any other irrep, you are going to get 0. So this is a general result for the last column of the character table of any SN. Now we can go ahead and figure out many more other results using the graphical method, and some of those are things we are going to explore in coming lectures as well. But before we do that, the major thing that we need to do in the next lecture is establish a proof for the Frobenius formula from which the graphical representation has been derived, as well as give proofs of things like the hook length formula and other useful results. Of course, that is not all that you need to do. You also need to talk about the way in which the matrices for the irreducible representations can also be figured out using a graphical technique, but that will have to wait for a later lecture. Bye for now.